Welcome to qnawire.
In this problem, we have to find the distance between a car and the very tip of an inverted cone, labeled here, if we assume that it is traveling in a circle around the cone and that there is no force of friction. So this is really just a banked curve problem. We don't actually need the second side of the cone. What this problem comes down to is just a scenario like this, which we've seen before in many other banked curve problems. Now, when we draw the forces for this, we can see that we, as always, have gravity pointing straight down, as well as our normal force perpendicular to the surface. Now, that normal force is going to be split into two components. A vertical one, Fy, as well as a horizontal one with our angle theta right here. I'll just label in red. Now, we can see that our y component of our force, or our normal force, must be equal to mg, right? Since it's pointing straight up, countering that. And we can also see from our diagram of theta that that force must be equal to our normal force times the cosine of theta. Now, using the same logic, we can see that our horizontal component, which is equal to Fn times sine of theta. And since we are moving in a circular motion, and this horizontal component is pointing straight inward towards the center of that motion, it must be equal to mv squared over r. Now, from our first equation here, we can see that Fn is equal to mg over cosine theta. So we can plug that into our second equation in order to get that mg times the tangent of theta is equal to mv squared over r. And now we have all the parts that we need to solve for our radius. We can cancel out our masses, and we get that r is equal to v squared over g tan theta. All right, the other thing to consider is that we are not actually solving for r in this case, right? The problem asks us for specifically d, which is this portion parallel to the slope of the curve. R would be, I'll draw it in green, this line down here. So what we are looking for is actually what we are looking for is d. And we can see from the setup of this problem that r must then be equal to d times the cosine of theta. And we plug in the same math that we had earlier. All that's left to do now is plug in our numbers. D cosine of 40 degrees is 34 meters per second squared divided by 9.8 meters per second squared times the tangent of 40. And when we solve for this, we get that d is equal to 183.502 meters. And that is equal to our final result.